The universe, at its grandest scale, is built on a promise of uniformity. We call it the cosmological principle. The assertion that no matter where you look and no matter how far you look, the cosmos is effectively the same. It is isotropic and homogeneous. There are no special places, no preferred directions, and certainly no giant scars disfiguring the face of deep time. This principle is the bedrock of modern astrophysics, the assumption that allows us to model the evolution of 13.8 billion years of history. But when the Planck satellite turned its sensors toward the southern hemisphere, sweeping the sky with unprecedented precision to map the oldest light in existence, it found something that violated this promise. It found a monster. Lurking in the data of the cosmic microwave background, the thermal afterglow of the Big Bang, is a region that defies the statistical laws of the Standard Model. It is known as the cold spot. While the rest of the CMB is a masterpiece of thermal equilibrium, fluctuating by mere parts per million around a baseline temperature of 2.7 Kelvin, this specific patch of sky is significantly, impossibly colder. It represents a temperature drop of roughly 70 microkelvins. To the uninitiated, 70 millionths of a degree might sound trivial, a rounding error in the firmus of creation. But in the precise Gaussian statistics of the early universe, this deviation is a screaming siren. It is a statistical outlier so severe that the Standard Model predicts a feature this large and this cold should essentially never happen, or at best is a 1 in 50 fluke that makes cosmologists deeply uncomfortable. For decades, the primary instinct of the scientific community was to find a prosaic explanation, something local and messy that was obstructing our view of the primordial fire. The leading contender was the Eridanus Supervoid. The logic was elegant in its simplicity. Imagine a vast region of space, roughly 1.8 billion light-years across, that is significantly underdense, containing far fewer galaxies and dark matter than the cosmic average. When a photon from the CMB enters such a void, it falls into a gravitational well. As it traverses this vast emptiness, the expansion of the universe, driven by dark energy, stretches the void, flattening the gravitational hill the photon has to climb to get out. The photon exits with less energy than it entered with, a phenomenon known as the integrated Sachs-Wolf effect. It effectively cools down. This explanation felt safe. It preserved the Standard Model and simply posited a large, empty structure in the foreground. But as our maps of the local universe improved, the safety of this theory began to crumble. 2024 analyses of galaxy surveys in the direction of the cold spot have revealed a troubling discrepancy. While there is indeed a void in Eridanus, it is neither deep enough nor empty enough to account for the full magnitude of the temperature drop. The math implies that the supervoid could explain perhaps 20 or 30% of the cooling, but not the freezing 70 microkelvin chasm we observe. The anomaly remains. We are staring at a feature that is too big, too cold, and too statistically improbable to be explained by the distribution of matter in our own universe. We are left with a persistent chill that refuses to warm up, suggesting that the cause is not a trick of the foreground, but a fundamental feature of the background itself. The cold spot is not a shadow cast by something in front of the light. It is a feature of the surface of last scattering itself, a relic imprinted at the very moment the universe became transparent. And if the structure of our universe cannot explain it, perhaps we need to look beyond our universe entirely. If the cold spot cannot be explained as a void within our reality, we must confront the possibility that it is a wound inflicted upon it. This demands we leave the relative safety of standard cosmology and venture into the high-energy frontier of string theory and eternal inflation. In this framework, the Big Bang was not a unique, solitary event. Instead, it was merely the nucleation of a single bubble within a vastly larger, rapidly expanding medium, often called the quantum foam or the bulk. Eternal inflation posits that space itself is constantly expanding at exponential rates, driven by a high-energy vacuum state. In this boiling ocean of potentiality, quantum fluctuations cause parts of the vacuum to decay to a lower energy state, stopping the inflation locally and forming a pocket universe. Our entire observable cosmos, with all its galaxies and stars and history, is just one of these pockets, one bubble floating in an infinite effervescent bath. Usually these bubbles are separated by rapidly expanding domains of inflating space, ensuring they remain isolated forever. But the math of eternal inflation allows for a terrifyingly violent exception: collisions. Just as soap bubbles in a sink can bump into one another, two pocket universes expanding into the same region of the high-dimensional bulk can crash. Such an event would be the most cataclysmic occurrence conceivable, a collision not of matter, but of spacetimes. Theoretical physicists have calculated exactly what this cosmic fender-bender would look like to an observer inside one of the bubbles. It wouldn't destroy the universe entirely, but it would leave a permanent mark. The collision would generate a shock wave, a circular discontinuity in the density and temperature of the plasma filling the early universe. This brings us back to the southern sky. The collision hypothesis predicts that such an impact would leave a circular spot of lowered temperature on the cosmic microwave background, a scar exactly like the cold spot. But a temperature drop alone is circumstantial evidence. To move this from speculation to science, we need a fingerprint that a mere void could never forge. That fingerprint lies in the polarization of light. A collision between universes would not just cool the photons, it would twist them. The immense gravitational stresses at the impact site would generate a specific pattern of polarization known as B-modes, arranged in a distinct vortex-like structure around the center of the cold spot. This is no longer purely theoretical. We are currently on the verge of testing this hypothesis with hard data. Next-generation instruments, like the Simons Observatory in the Chilean Atacama Desert, are being calibrated to hunt for exactly these polarization signals. They are looking for the cosmic bruise left by a neighbor we have never met. If they detect this specific twisting pattern in the ancient light, the implications are shattering. It would be the first observational proof that the multiverse is real. It would mean that the distinct, isolated reality we think we inhabit is actually just one chaotic member of a crowded, crashing ensemble. The cold spot would cease to be an anomaly and become a window, a point of contact where the skin of our reality grazed against another, proving once and for all that we are not alone in the grandest sense imaginable. We are just one bubble in a boiling sea, and we have the scars to prove it.